Start the recording. Here we go. Okay. Oh, before I forget, so someone did text me about moving the test date, but then I don't know who it was. so that's hard. But also it didn't. I can't really make it work where it still benefits you. So I think we'll just keep it as is unless there's uproar, which is April 2nd.
I think it's on the first because I probably would show up and say, oh.
Yeah, no, yeah, yeah. Yes. Can you imagine if you forgot that you had a test on April 1st?
Yeah, and you get a text from.
You're like, nah, you're like, joking.
No.
So we'll see if that's okay, but that's been posted for the whole term, so I think you can kind of plan around it. Okay. I kept all the things that we did last day just so we could kind of pick a way through it. We started confidence intervals, which is kind of part one of inference. And we built a confidence interval around the proportion of American Facebook users who think Facebook categorizes their interests accurately. Yeah. And so we started off and we checked the conditions. And so this whole page is from last day, so you've already got it. But the conditions, the first condition that we check is independence. Okay. We are told that it was representative, which is the goal of the independence. And we also checked this kind of optional condition that n of 850 is less than 10% of all American Facebook users, right? So the independence condition, we have to assume that all our observations are independent of each other. And one way to ensure that is to make sure that you haven't sampled too much of the population. But that's kind of counterintuitive in my opinion. And so, so usually I skip that one. The sample size or the normality condition, so what allows us to assume that we have a normal distribution is if our n times p hat, or the number of successes, okay, is greater than or equal to 10. And then if the number of failures is greater than or equal to 10, then the conditions are satisfied. Okay. Which means that we can build a confidence interval around our point estimate, p hat. That's our best guess at what the population proportion is, p. Okay. And we were told, and we're just going to accept it as fact, it's on our formula sheet, the standard error, which is kind of going to replace the standard deviation, but it's still a measure of spread, but it's called the standard error of p hat, is the square root of p hat q hat over n. Where q hat is, of course, just 1 minus p hat. It's just the 1 minus the p equivalent. And then we spent some time talking about Z star. Now, Z star is the only thing that determines the confidence level, right? Communicates the 95% confidence interval or 95% confidence level to this formula, right? And we said, okay, 95% confidence interval, we need the central 95%, which we know is 2 standard errors away. But then we said, okay, let's get a little bit more picky and we can use the t-table. And this was the first time that we saw the t-table. And if you don't have one, do you have it? I brought them. Do you need one?
No, I don't think so. Sorry.
Looks like you got it.
It's 6 character sheets. So
this one? I do have extras. Yeah, it's just 1 page.
Yeah.
Yeah.
Okay, yes, I have it.
Nice. It'll say confidence level at
Yeah.
the top of the table. Nice.
So when we, like are doing these questions and everything, will the question like say which table to use?
No, so
It's like the key thing to know which table to use.
yeah. And so if you're building a confidence interval, you'll want to use this. Yeah. Just because it's a lot easier. You can use the Z table, but it's a lot more work.
Yeah.
Whereas this has already been done. Right. And so, and we did a quick example of building a 95% confidence interval without this table. So you can still do it, but it's a lot more work.
Okay.
Right? And so this, once you get the hang of it, you're gonna be like, ditch the Z table, I only want this.
Okay.
Right? So then, more specifically, we move out 1.96 standard errors from the from our estimate, our point estimate, which gives us a 95% confidence interval. And then we did our math, we plugged it in, we had our estimate 0.67 or 67%, and then we calculated our standard error, right, is 0.016, blah, 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 blah. Multiply that by 1.96 to move out 2 standard errors in either direction. And then we wrote out our interval, and then we ran out of time. So from here, I'm gonna add a page. So now I'll say new. Okay. So our interval, right? We're gonna move down a little, we're gonna move up a little from our point estimate, and you're always going to write it as a round bracket and your lower value, comma, your upper value, and then a round bracket again, which can be kind of tricky because you see the plus minus, and it just makes you want to do the +1 first. That's okay, as long as you list it in the second spot, okay? And so here, note that upper comma lower does not exist. So if you write them in the wrong order, I will take half a mark off because it doesn't exist. Yeah. I know, so picky. Gonna raise you right. So from your lower value to your upper value, okay? This is pretty fun. Kind of once you've picked apart all the information that you are given in the question, you've figured out what type of question it is, right? A one sample proportion question. And so, and that's all we've seen so far, and that's all we will see for another week. Okay, so we'll only work and we'll learn all the skills with this one type of question. And then when you're ready, then we'll start introducing other types, okay? So for now, just one sample proportion. So this is half the work, thus half the marks. Usually I do about 2 marks here. 2 marks out of 4. Math is fine. You can get software to do it, right? Excel will make you a confidence interval. And so that's only half the marks. The other half of the marks is the interpretation. Okay? And so whenever we build a confidence interval, we need to interpret it. So many exclamation marks. It must be Friday. Ah! Yeah. So we're going to use a standard interpretation. Okay. And I want you to use this exact sentence structure. Okay. And so I know that it gets weird. Well, isn't that, plagiarism or whatever? No, no, not in this case. I want you to use this exact sentence structure. So for any, and that's the beauty of it, for any confidence interval, we use the same sentence structure. Sentence or interpretation. Yeah. It's going to be one of those things where it's probably easiest to just memorize it, right? Until one day it'll click, right? And you'll say, oh, sure, that makes sense. The sentence or the interpretation is going to go like this. I like the we kind of collective. We are some percentage. Now, usually, 95%. Well, that looks weird. So we're blank percent confident the interval from blank to blank. So from the lower to the upper value of your interval, of course, captures. And we'll talk about the importance of that word there, but for now, just absorb it. Okay. Captures the true blank. I know. Here, this is going to be the parameter, okay? But you are just going to reword the question as an answer. Reword the question as an answer. The question is going to have to ask you, hey, build a 90% confidence interval for the proportion of people who feel that their interests were represented accurately, right? Something like that. So for us, for this interval, for the confidence interval we built, it's going to look like this. We are 95% because we built a 95% confidence interval. We are 95% confident the interval, oops, I'll show the interval from, now these are proportions, so you could convert them to percentages if you want, or I'm just going to keep it as a proportion, maybe to 3 decimal places, let's say. And so the interval from 0.638 to 0.702 captures the true. Now, the true, you can kind of outgrow that eventually, but this is to indicate the population. It's very important that you talk about the parameter, right? The population proportion. Okay? And so if you say the true proportion, then that means the population proportion. Okay? The true, and here's where we just grab and rephrase the question as an answer. And it's kind of usually long and annoying, but not hard. The true, it's So I rephrase the question in a way that I would ask the question on a test. Okay? And so it said construct a 95% confidence interval for, and because it's our first one, I even have the true proportion of American Facebook users who think Facebook categorizes their interests accurately. Okay? And so from here, the true proportion of American Facebook users who think Facebook, I think it's so funny that she's got the Facebook. Facebook categorizes their interests accurately. So here. Just to match them up. So you just rephrase the question as an answer. And maybe I'll white that out. I'll make it obvious. I took some stuff out. Okay. And so this is another 2 marks out of 4. All right, so that's the remaining 2 marks. People love to forget to interpret the interval, but then you only get the half marks for building your interval, right? Our job is kind of twofold. Right? Don't worry, the question will say interpret the interval, but everyone forgets to do it for some reason, even though I feel like I say it a lot. Stressful writing a test. Okay, nice. So going back to why we use the term captures. So now this sample proportion and everything that we used to build this interval, right? This 0.67 was built off of a sample of size 850, a random sample, a representative sample, right? But if we went and collected a brand new sample of 850 American Facebook users, right? This number would be similar, but not quite the same, right? And so there's variability there. And so that's why, right, this estimate or our point estimate, right, is going to move around, and it's going to, we don't know if it's a good estimate or a bad estimate. There are times where we collect a random sample, and just by random chance alone, this point estimate is very different from the population. We don't know that, right? And so that's why we're only 95% confident, okay? Because if we have from the central limit theorem, which we introduced last day, but if we have our p hats are on this normal distribution, right, centered on the population proportion, but what if our p hat was way out here? Even if I built an interval around it, I'm not actually capturing this population proportion. And so how I like to think of it is if the stapler is the population proportion, it exists, right? It's some number. If we were able to collect information from all American Facebook users, we would be able to find the population proportion, right? But we don't need to because we have statistics. Okay? And so, but this value is fixed, right? And so when we're saying, okay, we're 95% confident that this interval captures what's going on is our sample, right? And so now I'm my sample, my point estimate, most of the time, right, depending on how I move around, but sometimes 5% of the time, we don't capture the population proportion, but I don't know that about my sample, right? And so that's why we're only 95% confident. And that's why it's so important that you say captures, right? Or some other indication that you understand that the population proportion is fixed, right? And so for kind of training wheels and honestly, just in life, if you just use this blurb, the standard blurb all the time, then you're safe, because there's a lot of different ways that you could interpret it incorrectly, and I don't want that. And so here it is. I guess you could get wild and crazy and say we're 95% confident the true proportion of American Facebook users who think Facebook categorizes their interests accurately is captured by the interval from 0.638 to 0.702. Whoa. But I like to get the numbers out of the way and then just rephrase the question as an answer. Really only two ways that you can interpret it. Okay, nice. Any questions so far? I do trust that you would ask. So like we were saying, what does 95% confident mean? Suppose we took many samples, right? Like we did. So you're kind of building off of a sample, but you don't know if it's actually representative or capturing that population proportion, right? And so then if you built a bunch of different confidence interval, about 95% of those intervals would contain the true population proportion, P. Bless you. And so that's a task for Excel. And so you'll have an Excel assignment kind of walking you through the central limit theorem and confidence intervals. So the width of the interval, that's how confident we are that we're going to capture this thing, right? And so if I make my net wider, right, or my bounds wider, then I'm going to be more confident, right? But then I lose that precision. Okay? And so if we want to be more certain that we capture the population parameter, so increase our confidence level, right, we would need to make a wider interval, but it comes at a cost. But it's less precise. And so 95% is the default confidence level. Because it is a reasonable trade-off between confidence and precision. And precision. So there's a Garfield. Taking a look at tomorrow's weather, the high temperature will be between 40 below zero and 200 above. This guy's never wrong. It's true. Not very informative, though. Right? And so that's why 95% tends to be the industry standard that you report. Okay. We already looked at how we find the Z star. So changing the confidence level, as we saw, that's going to be done by this Z star, this critical value. Z star is called a critical value. And so we can change Z star by using the table, and I'll bring it in just so we can have a refresher, but some commonly used confidence levels are 90, 95, 98, and 99, right? And 95% is your go-to 1.96. Of course, with the Z distribution, so with the Z table, you could build any confidence level you wanted. So for example, let's pick one that's not on the table. As we saw last day, let's say I want to build a 97% confidence interval, right? Then I'm going to have some negative Z star and a positive Z star that makes that happen. Right? We've done work practicing how to find these values already, right? That was before the break, but still. So if I have 97% in the center, that means I have 3% left over, which means I have 1.5% here and 1.5% here. These Z's are going to be the same. So once you find one of those, the negative Z is probably the easiest, right? Then you can drop the negative and you know by symmetry that the positive Z star, which is the one we use. You could use the negative, but in the plus minus, it would reverse them, and maybe that is helpful, but just a lot to think about. So what would you do if you had to build a 97% confidence interval? You'd have to find the value in the table entry. Oh, I think I did one too many zeros there. Table entry closest to 0.015 in the Z table. 0.015, it should be on the negative side. 0.0107. Bang on. Which means that we would need a Z star of 2.17. For a 97% confidence level, or let's just do CI. We need Z star 2.17 from the Z table. We usually use the T table instead to find Z star. So if I bring in that new table, or just the snippet that we're going to be working with, right? So the T table looks like this. And for now, we're going to ignore the degrees of freedom, right? But we'll introduce those. But slow and steady wins the race here. But down at the bottom, we have a Z star line. That sounds appropriate. So let's go here, copy this in, and I'll crop this. So it can be cleaner. Okay, so here you've got your confidence level, and it's going to map down to its Z star. Right, and so we saw 95% confidence interval. We're going to use a Z star of 1.96. 98% confidence interval. We're gonna go here, search for 98, and then 2.326, which she only has 2 decimal places, but that's okay, 2.33. I do expect you to use this table. All right. If you decide to use the Z table because that's what you're more comfortable with, just say using the Z table, I find that this Z star, because the Z table only gives you 2 decimal places for Z, right? But here we get a little bit more precision with 3 decimal places, and so that's nice. And what you'll find is your homework questions use the 3 decimal places, and so it usually doesn't matter, but sometimes it makes a difference and it marks it wrong. Okay, so here, wink. That didn't look very nice. Looks worse. Oh well. I guess we can just briefly talk about what these values mean. A one-sided P tells us the area in one of the tails. Okay? And I only bring it up because we're going to introduce this concept today, so it's time. So the one-sided P is going to be the area in one of the tails, okay? Whether it's the upper end, so looks like this. Our Z is still centered on 0. Yeah.
Can the P's, so the P's can have like different numbers on the start?
Yeah, but they match up with the percentage up top here. So let me show you. If we're forcing 98% in the center, you have 2% left over, right? But they have to be split evenly between the tails. So you've got 1% here, and you've got 1% here. So all this is saying is that, okay, fine, the area in one of the tails is 0.01, so 1%. And if you're interested in both the tails, adding up the tails, then it's 0.02. No? And that's there, demystified. Now, there's a little bit more that we'll do with that, but that's all it's saying. Okay. So this is one tail has area 0.01. Both tails have area 0.02. And this is from or at Z equals negative 2.326 and Z equal to 2.326.
Sorry, what does that say? The yellow boat?
Both tails have area 0.02. So there will be instances where we're interested in just one of the tails, and some instances, most instances, where we want to find the area in both the tails. Because what is the area under the curve? The area under the curve is a probability, right? And so the area in the tail, let's talk about the upper tail, right, is the probability of being more extreme than a Z of 2.326, right? And so it's the probability of seeing something even more extreme than this Z. And we're going to start to call it the p-value, which is why it's called the one-sided P and the two-sided P. But that's in hypothesis testing, which is the next section, which we're starting today, but it takes a while. But they are linked. So confidence intervals, as we've established, they're always about the population. You know everything there is to know about your sample, right? You know your sample proportion. You're 100% confident that the sample proportion is this, right? But we're trying to learn about the population. Okay, so, and they're not probability statements, right? Because the population proportion, I point at the stapler, is fixed, right? And so that's my population proportion, it's fixed. And so, so it's more about how confident I am that I'm able to capture it. Yeah. And so, blah, blah, blah. Unbiased estimators, we don't need to know about that. So like we saw, here's kind of a visual of what does 95% confident mean. And so here, I'm going to change this to the proportion, since that's what we're talking about. Contain the true proportion. I don't know where she got that example from. Exclusive relationships, going steady. So like we said, so let's say you took many samples, right? We don't do this, but what you would find is that each p hat, right, would move around. So this little dot represents your p hat, and then you build an interval around it. But the interval, a 95% confidence interval, right? It takes, you move out 1.96 standard errors, and the standard error uses this p hat, right? P hat, q hat over n, and then square root it, right? And so it's all based off of this p hat. And so then you move around, and sometimes, unbeknownst to you, you get this p hat that's kind of far off of where you expect the rest of the distribution. And that can happen by random chance alone, right? And that's why we're only 95% confident. Nice. But any questions about confidence intervals before we get into hypothesis testing? Yeah. Okay. I X these because we didn't, it says remember when, but it was never introduced, so we'll skip those. But hypothesis testing for a proportion, we're going to call this type still one sample proportion. And hypothesis testing is a formal way of drawing conclusions about, well, I hate to say hypothesis, about a hypothesis. That doesn't really help, does it? What's a hypothesis? I think back to, I think it was like grade 9 science or something where, or maybe it was even younger, I don't know, where we had to come up with some hypothesis, right? I believe that there's more pollution on the highway than on this back road. And then we went out and tested it, and it was true. Well, we need a little bit more kind of formality there, but we're doing the same thing. And so we have an idea. So a hypothesis is an idea or a theory about the population. hypothesis testing is a formal framework that allows us to draw conclusions about our hypothesis.
A formal what? Is that what it
A formal framework. Framework. I'll try again. Framework. Looks the same. So if you're reading kind of scientific journals and things like that, then anything that's published has to be done with a hypothesis test, or we're kind of moving towards using confidence intervals. And so I'll introduce kind of how you can use a confidence instead of a p-value. But as you saw, they're linked, right? And so we'll be able to kind of move between the two. But I'll introduce the formal framework because that's my job. And hypothesis testing is the reason that if you have to take this course for whatever program you're in, hypothesis testing is the reason you have to take this course. Okay? And so what's kind of fun is, although there's a lot of kind of ins and outs and things to keep track of, once you learn the rules, like I was saying, we're just going to learn rules of this complicated game, but then you'll be able to play all the expansions. Does that make sense? So, I love playing board games, so I'm a gamer. I like to say that I'm a gamer, but only board games. I don't play video games. I think if I tried it, I would probably like it, and that's probably the problem. But complicated board games, that's my jam. So what I want to do is just give an overview of what hypothesis testing looks like, and then we'll go back and we'll fill in the gaps. And then with an example, we'll go back and we'll kind of fill in some more gaps. Okay, so it's going to take time. You're going to need to be patient. And eventually, right, then we'll know all the rules. So hypothesis testing or HT, as I'll call it, has 4 steps. I break it down into 4 steps, depending on kind of who you're talking to. You could break it down into 7 steps, but I think 4 is kind of a nice number. I guess kind of step 0, I know, rude. You have to check the conditions, but let's ignore that for a while, because that's not the most important part of what I need you to learn. So step 1, check the conditions. Well, the conditions that you have to check depend on what type of question you have. And so we'll just kind of parking lot that for a little bit. But step 1 of a hypothesis test, well, if you have some idea, right? If you have an idea or a theory about the population, then step 1 is to state what you think that is, right? And so step 1 is to state the hypotheses. Now, in your work, you don't have to list the steps. You have to do all the steps, but you don't have to actually outline which step you're doing. But I do think it's probably helpful. And I'll always write out what the steps are, just so you can see that it's always the same. And so step one is to state the hypotheses. Now, what's going to happen is if you have some idea about the population, right, there's a chance that you're wrong, right? And so what we call the null hypothesis, we denote with a capital H subscript 0. This is called the null hypothesis. Yes. There's a ho and a ha. So the null hypothesis, because 0 is null, right? H naught, so 0 is not, or H naught, right? It's usually how I pronounce it, H naught. Because a subscript 0 is not or null. This is a statement. Okay, and so it's really important that you use a colon and not an equal sign. Okay, has to be a colon because it's a statement. Colon, since it is a statement. The statement has to be about the parameter. Okay? And so it has to be about the parameter. And our hypothesis, the null hypothesis, has to have an equal sign in it. So before you even start, you can just jot down an equal sign, because half the work is going to be figuring out what type of question you have and then setting up your null and alternative hypotheses. And then everything else after that just kind of flows with enough practice. And so here, the null hypothesis is about a parameter. I'm going to leave it like that. You'll see why in a sec. So my null hypothesis, I always have to assume that that my population proportion is the number that I think it might not be, right? Or I have to assume that two things are the same until I have proof that, okay, that's very unlikely that they're the same, right? And so then I vote in favor of my alternative hypothesis. I use HA. You can use H1 if you want. This is your alternative hypothesis. Or H1. I think in biology, they like to use H1, H0, H1, but I like HA. Again, a colon because it's a statement. This is usually the thing that I suspect is going on. Right? And so here, these values have to be the same. Right? Whatever it is I'm hypothesizing about, my alternative has to be about the same thing. Right? So these values must be the same. Values in H naught and HA must be the same. Must be same, must be the same. This is usually not equal to. Yeah. We're going to have a couple of different options here. But let's start with the not equal to. That's your default. Now, often, not always, but often, HA, or the alternative hypothesis, is the thing that we're trying to prove. The thing we're trying to prove. But we have to do all our testing assuming that the null hypothesis is true. But we have to assume H naught is true until we have enough evidence against it. Now, you bust out your formula sheet. The first part, so once you've decided that you have a one sample proportion, which is what we will have in the next couple of days here, and so we're safe to just kind of jump here. But if you're doing a hypothesis test for P, right, then our hypothesis is about the population proportion, right? I use my sample proportion to learn about my population proportion, and then I tell you, hey, here's your null hypothesis. Might be nice to have, right? And I also give you the next step. So let's just grab these here. Whoa. Why did it jump here? Oh no, okay. So on your formula sheet, right, for one sample proportion questions, for one sample proportion, I give you that H naught is always going to be, how does P, the population proportion, I have to assume that it equals some number. Okay, so I have a P naught, but this P naught is a placeholder. Placeholder. So PO, or P naught, is a placeholder for the proportion, the number that you want to compare your sample proportion to. For the number you want to compare your sample proportion to. Okay. This will be given in the question. Okay. This will be in the question. If I've given you, why don't I give you the HA? Well, because what we saw here is if we have H naught is that P is equal to P naught, whatever that number is, right, generically, then my alternative hypothesis, well, I have to talk about how P relates to P naught, right? You can't say, oh, I have to assume that my proportion is 0.4 and therefore it's greater than 0.6. What? That doesn't make sense. All right. And so here, these two things have to be the same. Right? And so it's kind of redundant to put the alternative hypothesis on your formula sheet because it'll be the same. The only thing that changes is as a default, that it's not equal to this number. We will be able to say, okay, P is less than P naught, or maybe we're interested in P being greater than P naught. But for now, let's just focus on the not equal to. Because that's the default. So if you're ever struggling, so this will also be in the question. If you're ever struggling with, okay, I don't really know which sign to use here, then your default is going to be the not equal to. And that's the safest option. And that's why it is the default. Okay, that's a lot about your null hypothesis, but it's an important part of the problem, right? Is stating your hypotheses. In terms of marks, stating your hypotheses, usually a hypothesis test, if I exclude the checking the conditions, I would say it's 7 marks. And so let's do this here. So a hypothesis test is usually out of 7 marks, Z marks, 7 marks. And your null and alternative hypothesis are a full 2 marks. The reason for that is because then this is where you tell me how you've interpreted the question, right? From when I read the question, this is what I have to test. And as long as you follow through with that, right, then I'm okay with that, right? And so a lot hinges on what you said your hypotheses were going to be, right? So there's a lot of marks in your null and alternative hypotheses. Okay. Broad strokes, as promised. And then we're going to go back and we're going to fill in the cracks. We're going to just smooth over and smooth over. But from here, we're going to have a pretty good idea of, okay, I want to test this theory. And step 2, I call it do the test. Just because it's catchy. Do the test, do the do. Or more boring, calculate the test statistic. Blah. To calculate the test statistic is going to be how far is your statistic from the hypothesized parameter? From the hypothesized parameter. In general, your test statistic is always going to have the form. So your test statistic is going to be your point estimate minus your hypothesized value divided by the standard error of the point estimate. We've seen that before, right? We see We've seen Z is X minus mu over sigma, right? How far is X from mu if the spread is sigma? We're gonna branch out a little bit, but if we think about from the central limit theorem, we saw that, okay, P hat follows a normal distribution centered on P with a standard error of PQ over N. If we don't know P, because we don't, then we, in the confidence interval, what do? We just replaced it with hats, P hats. And so then for one sample proportion, we'll be able to calculate a Z because it came from a normal distribution. Z is going to be P hat minus P naught. How far is my sample proportion from my hypothesized proportion? If the spread, and this is where it gets a little bit weird, is P naught Q naught over N square rooted. I don't expect you to keep track of that. It is on your formula sheet down here, which kind of guides you towards your second step. On your hypothesis test. So the first two steps will always be given on your formula sheet. The reason we use P naught is if you're okay to just accept it, that's great. But it's because we assume the null hypothesis is true, right? And so in that case, the null hypothesized value is a better estimate for the population proportion than our P hat, right? We assume that this is the true center. And so then it's a better estimate. Okay? But that's the only reason. Okay. So do the test. Step 2, do the test, or more boring, calculate the test statistic, right? Is going to be calculate this Z for now. This calculation, right? What you're calculating changes. And if you glance at the formula sheet, right, here we are at one sample proportion, but then very exciting day when we move to 2 sample proportions, the next page, right? We can build a confidence interval. We can do a hypothesis test. We can calculate a Z. A little bit more complicated, but it's because we have 2 groups now, right? Kind of need to keep track of 2 things. And then our test statistic becomes a chi-squared and so on and so forth, but all in good time. So at this point, and we spent a lot of time calculating Zs and finding areas under the curve with Zs. And so this Z behaves the exact same way as the Zs we've been seeing. And this is usually just 1 mark. What? So much work. It's just math. And usually we would make software do this calculation anyways. We have to do it by hand, but usually. And the reason I only do 1 mark here is because the math is fine, right? Even if you do a little typo, as long as you follow through with the Z that you tell me you get at the end, then that's fine, right? So just follow through, that's good. Step 3, although it is possible to say, okay, right, imagine you're trying to explain to your boss, hey, I don't think that my sample came from a population centered on P naught because my sample proportion is 3 standard deviations above my hypothesized value. And they would say, that doesn't mean anything to me. because that's hard to kind of understand. So then we say, okay, well, what that means is the probability of seeing something like this, if P is equal to P naught, is very, very, very small, right? 0.0001, let's say, right? So then we attach a probability to this Z, okay? And so here, step 3 is going to be find the p-value. The p-value, let's define it first. The p-value, and you don't need to memorize it, but it might help. The p-value is the probability of seeing something as extreme or more extreme than what we saw in our sample. Assuming the null hypothesis is true. Assuming H naught is true. Notice that this is generic, right? It doesn't talk about a proportion, a sample proportion, right? And so for one sample proportion, this becomes more specifically, right? The probability of seeing a p hat as extreme or more extreme than what we saw in our sample, assuming that P is equal to P naught is true. So the p-value for this case is the probability of seeing a p hat as extreme or more extreme than what we saw in our sample, assuming H naught, which says that P is centered on P naught, oops, is true. A probability is an area under the curve, right? And we have a normal curve because Z comes from a normal curve. And so the probability is really the area under the curve. And something as extreme or more extreme, that puts us in the tails, right? As extreme or more extreme. More specifically means the area in the tails. So instead of trying to communicate to your boss that if I assume that P is equal to P naught, which is some number that I want to compare my sample to, right? And I saw a P hat up here. Instead of trying to say, oh yeah, it's 3 standard errors away, so yeah, pretty unlikely. Possible, but unlikely, right? And maybe I should move this guy, move this little guy out here, more into the tail. That's hard to communicate, right? This is going to be Z standard errors above P naught, but although you could, right, that's hard to communicate. So it's easier to talk about the probability. This is the p-value. And what we say when we're only looking at one side, we call it a one-sided p-value. It's all coming together now. Right. The area in one of the tails is a one-sided p-value. Okay. When HA is that P is not equal to P naught, we say we have a two-sided test. Our sample is only going to pop up in one of the tails. But we would be equally concerned if it was the same distance in the other direction, right? And so then we say, so when we have not equal to, I'm concerned about both of these tails, which means that I need to pretend that this area could also happen down in the lower tail or in the opposite tail. So then let's do, I'm just going to copy this. Copy. Paste and make it smaller so that I can, because then we also would be just as concerned if P hat was down here. Also Z standard errors below P naught. Then your p-value is in both the tails. A couple of ways you could do it. You could find the one-sided p-value and then multiply it by 2, right, by symmetry. So here's another one-sided p-value. So then what we call the two-sided p-value. Oh, bless you. The two-sided p-value is the one-sided p-value multiplied by 2. One-sided p-value multiplied by 2. I think you already have some idea of how to find the p-value, right? Because if you have a Z, right? And this Z behaves the same way that all the other Zs did that we were working with. And so then if you have a Z, now you know how to find probabilities associated with Z, right? And so, right, you could use the Z table. Find the area in the tail, as long as you remember, okay, I want the area in the tail, or we're going to kind of level up and start to use the T table, but it behaves the same way. Okay? But I'll show you both. Okay. Now, the probability of seeing, so if we think about the p-value as, okay, the probability, it is the probability of seeing a p-hat as extreme or more extreme than what we saw in our sample, assuming that it is centered on P naught, right? So at some point, we're gonna have moved far enough away from this P naught to say, okay, possible, but unlikely, right? And so then we're better off saying, you know what? I think that that's evidence against my null hypothesis, or I should go here, right? So we did all our testing assuming that the null hypothesis was true, but then we found the probability of this being true is really, really small, right, from the p-value. So then we say, okay, that's evidence against H naught. And usually that means that you would reject H naught in favor of HA. So what's small enough? Small enough, right? If your p-value is small enough, then you have enough evidence to reject H naught. So this brings us to, and this p-value, finding the p-value, although it's quite a bit of work, and 1 mark. Because again, if you flub it in some way, right? Or even if you forget how to find the p-value, that's not, that's not the skill that I need you to have. The skill that I need you to have is the conclusion from the p-value. So even if you're totally blanking, you would say something like, I'm going to use a p-value of 0.02 or something reasonable, right? And so say, hey, I totally forgot how to do this. I'm going to go ahead and draw my conclusion with a p-value of this. 0.02 is probably good, right? And so it has to be reasonable. Okay. You don't get this mark because you made it up, but you can still get the 3 marks for the conclusion in case you're tracking, right? And so step 4 is the conclusion, right? This is what I'm most concerned about, right? That you can leave this course and be able to take a p-value and draw some conclusion, right? And so this is 3 marks. Because there's 3 parts. I know, step 4 has 3 parts. It's like when students ask me how many questions there are in a test, like I could do 1 with 1 billion parts. Doesn't matter. What's it out of? Well, I could make every question out of 100. Doesn't matter.
You answer the first one, then it's like it pops up like 5 others. It's like, oh.
I know those. So when I built those Excel assignments, because they have to reference the same data, then there's no way to generate randomized data and then have you be able to answer. So that's why it's many, many parts. I know, so rude. So rude. Well, does it tell you? It tells you how many parts there are though, right? Yeah. I think it says like part 1 of something. So at least you kind of know. But can you imagine it just keeps going. Sometimes I get carried away when I build those. Okay. All right. So your conclusion. We need our p-value because it helps us communicate how likely or rather unlikely H naught is. Okay. And so in kind of broad strokes, it goes like this. Our conclusion says that if the p-value is small enough, and of course we'll have rules for that, but if it's small enough, and thinking about the p-value, the probability as the probability that H naught is true, right? That's not exactly correct, but it is a helpful way of thinking of the p-value. Okay. And so the p-value, so if the p-value is small enough, we have enough evidence to reject H naught in favor of HA. If I tell you, okay, thinking about our null hypothesis that P is indeed centered on P naught, and the alternative is that it's not, it doesn't tell us what it is centered on. It just says, okay, once we compared our sample to this P naught, we found that kind of unlikely. So then we found that if the center is at P naught, then I found my P hat to be out here. So then my P value is the area in both these tails because I have not equal to, right? So I just allow it to potentially happen in the same way in the other tail. So what happens is as you move further and further away from your P naught, right, then this P value gets smaller and smaller and smaller and smaller, right? And so that means if the P value is small enough, right, we need some threshold where, okay, if it's smaller than this, then it's unlikely that H naught is true. Okay? And so here I'll make a note. We can think of the P value. I don't want you to say it like this, but we can think of the P value as the probability that H naught is true. We have some region here where we're fine to say, okay, it's basically P naught, right? But then at some point, we cross this threshold and we say, okay, yeah, probably not. Could be, right? Because remember, these tails go to negative infinity and positive infinity in theory. And so then, okay, all these sample proportions could happen, right? But they're just unlikely, okay? And so the threshold that we use, the threshold is called the alpha level. Or significance level. So the alpha level, so this is a Greek letter alpha. It is a fish. The alpha level is called, is called the significance level. There's a move towards calling it the discernibility level, but I think that's really confusing, probably mostly for myself, because I've called it the significance level all my academic life. And so that's going to be really hard for me, but so I'm going to keep calling it the significance level. I will add it here though, or discernibility level. So the alpha level is the significance level. And the default alpha level is 0.05 or 5%. If I don't tell you what alpha level to use, then you use 0.05. Okay. But sometimes just for getting flexy, it'll say use a significance level of 0.1 or 0.01. Okay. So possible alpha levels are alpha equals 0.01, alpha equals 0.05. Sorry, I should say common. You could use any alpha level that you want, but some common alpha levels are 0.01, 0.05, and 0.10. Which one of these makes it the hardest to reject H naught? Which of these makes it the hardest to reject H naught? Let's draw it out. If we focus on one tail, right, that's going to be easier, because if we have a two-tailed test, so a not equal to, then this area gets split between the tails. But let's just focus on one tail. And let me make a better normal distribution. Focus on or use one tail. It behaves the same, but you'd split it between the tails, but that's a little too complicated for us right now. So in the upper tail, let's work there. I don't like the lower tail. I like the upper tail. If you had to draw a line where the area in the tail is 0.01, let's draw, let's do an orange line. I would draw it somewhere here. I'm going to force this area to be 0.01. If alpha is 0.05, then I have more area in the tail, right? And so now I can move in a little bit. And I'm just doing it to visualize. Doesn't have to be exactly to scale, as long as you're drawing it in the tails. And let's see here. I kind of like to use, what color can I use? Purple, maybe. Which means that alpha equals 0.10 is the closest. So our p hat is going to fall somewhere on this line, right? And so once you've passed this threshold, then the area in the tail is less than the alpha level, right? And so then it is small enough, which means we would reject H naught. And so here, this area, right, we're going to end up rejecting H naught, depending on what level, right? But once you pass this threshold, depending on what you set it at, then you're going to reject H naught. Here, we're going to say we fail to reject H naught. When we say we fail to reject H naught, we're not saying that H naught is true. We're just saying I couldn't find any evidence against it, right? And so that's why it's important to use that terminology of fail to reject H naught. Whereas here we have enough evidence to reject H naught. So our P hat is usually if P naught is a reasonable guess at the population proportion, then we hover around here. But then we start to, just as we suspected, we start to see sample proportions that are out here in the tails, right? And so first stop, the easiest to reject is going to be where? At 0.1, right? And then slightly harder to reject it at 0.05. And then I would say the hardest to reject is at 0.01. Oh. Hardest to reject. Alpha equals 0.01. As an alternative to the p-value, we could give Z cutoffs here if we wanted to, right? You know how to find a Z that has 0.1 in the upper tail, right? And you know how to find a Z that has 0.05 in the upper tail, and you know how to find a Z with the 0.01 in the upper tail. Or kind of even better, what if we just use our table? New phone, who dis? So here, if we're focusing on one side, just for simplicity, this one-sided P, right, also gives us Z values that match up with these areas, right? These P values or alpha levels if you want. So if I have alpha 0.01, right? Oops, draw it on the wrong side. That's going to be the same as saying, okay, well, if my Z is larger, so past 2.326, then I have enough evidence to reject H naught, right? And so you can use this. This is called the critical value approach instead, where you use Zs to draw your conclusion instead of your p-value. It's nice to see, and you're welcome to use it if that makes more sense to you. But because the p-value approach is kind of the more common way of doing it, I will only use the p-value approach in class. But I will know what you mean if you want to explore the critical value approach. Z star is 2.326. Any Z beyond that, then I reject H naught. Right? What about 0.05? If it's just in one tail, my Z star is 1.645. Back in my day, we had to memorize this line and all the values. I don't think we had to do these first three, but 0.1. Z star is 1.282. So if my Z that I've calculated is past this threshold, then that also implies that the area in the tail, or the p-value, is less than my alpha level, right? And so they're the same. They're doing the same thing. But I like to do, if the p-value is small enough, right, which means we have to we found the p-value and we need to compare it to the alpha level, right? And so if it's less than the alpha level, then we have enough evidence to reject H naught in favor of HA. Turns out I did not need the slides today, or I didn't want them rather. So our conclusion is going to have 3 parts. The conclusion has 3 parts. And you have to talk about all 3 because they're 1 mark each. First, you're going to compare the p-value to the alpha level, right? It's either less than the alpha level or not less than the alpha level. Those are your only 2 options. Okay. And I want you to use the less than alpha and not less than alpha, and you'll see why in the sentence structure, why it makes more sense to do that. Okay. And so compare the p-value to the alpha level.
This is just very thought on this. I just think it's a little bit funny how stats use like alpha and sigma, and like you hear kids say, you know, it's like hearing like some kids who says like slang. I was like sitting here like reading and I'm trying not to giggle. My little brother's 6 and he always says.
That's so I've actually haven't made that connection. I'm like, yeah. But yeah, I don't know why they're using Greek letters all of a sudden. Greek letters are cool.
I think it might stem from kind of this like hierarchy of like alpha and beta males, and then people kind of take that slang and put other things.
Yeah.
That's a good point. Or like Amber just said like the frats using like
Oh yeah, yeah, totally. Yeah.
That's where
Yeah.
I guess it stems from. I don't know. My sister's turning 18 in like 2 weeks, so she's not really.
Kids. The second part is you're going to state the conclusion in terms of the null hypothesis. So the conclusion in terms of H naught. Again, there are only 2 options here. You either have enough evidence to reject H naught, or you do not have enough evidence to reject H naught. And I'm going to write out the 2 blurbs, the only 2 blurbs that you have to choose between. Okay, and so, but for now, let's just kind of talk about all the parts. Okay. And then finally, the one everyone forgets to do, which you're going to say, what? Why would people forget to do that? That's the whole reason, is the conclusion in terms of the question. But at this point, you're tired. You've done a ton of work. So then I reject H naught and then you move on. Well, what does that mean in terms of the question? So then your last mark is the conclusion in terms of the question. Seems easy now, but I have been tempted in the past to get a stamp that says conclusion in terms of the question, because I write it so many times. -1. So in terms of the first 2 parts, right? Option 1, oops, is if the p-value is less than alpha. Oops. It would go a little something like this. And usually I say 1-sided or 2-sided here, but I'll hold off on that because we haven't really talked about it. So since the p-value of, you always want to show off that you know what number you're referring to, right? And so someone should be able to read your conclusion and get all the information that you worked to get in the previous parts. And so you want to say of this. So since the p-value of whatever it is from the question that you've done is less than the alpha level of blank, compare the p-value to the alpha level. That's what this looks like. Since the p-value of blank is less than the alpha level of blank, if the p-value is small enough, right, which means it's less than the alpha level, you've moved out into the tails far enough. Since the p-value is less than the alpha level of blank, we have enough evidence to reject H naught. And if I'm rejecting H naught, you can say in favor of HA. You don't have to. In fact, I don't want you to bring HA into it until you feel really comfortable, because your conclusion has to be about H naught. We did all our testing assuming that the null hypothesis was true, right? And so you don't bring in the alternative until the very end. So we have enough evidence to reject H naught in favor of HA. That part's optional. Which means whatever the question was asking you. Now, I'm going to copy this. And I'm going to edit it. Have you ever thought about when you have to say edited it? I edited it. I edited it.
I say that shockingly often, and it bugs me every single time.
I know, I can't stop. I edited it. Option 2 is if the p-value is greater than alpha, right? So you didn't move into the tail far enough, right? Which means it's basically the same as p naught. And so since the p-value of everything stays the same is not less than the alpha level of blank, okay, we do not have enough evidence to reject H naught in favor of, and then H naught, and then usually I ditch the. It's not incorrect to keep it, but you'll be bored of writing at that point. Which means what? So not rejecting H naught means something in terms of the question. So that's why I like you to use the is less than or is not less than the alpha level, because then you can just tweak it and say we have enough evidence or we do not have enough evidence to reject H naught. Yeah. Nice. So one mark, one mark, one mark. All right. That's a moneymaker. So many marks. Okay. So here I X these because they don't really make sense. And we spent a lot of time talking about all this, blah, 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 blah. Let me just make a note, mostly to myself. Due on Tuesday. Oh, that's not when we meet. do on Wednesday. Because I didn't talk about decision errors, but of course there is a chance that we're wrong. But I want you to leave, or no, I don't want you to leave. I want you to try. The answer is in the slides.
So anybody have an exciting weekend plan?
Well, you'll be trying this on your own.
Yes, I actually will.
On your own for Wednesday. And there. All right. With that, I release you to your exciting weekend plans.
I have an exciting weekend plan. It's really sweet.
Mhm.
Like I don't really sleep.